Hello, welcome friends to our Smart Easy Mech YouTube channel. Our channel deals with all the mechanical engineering subjects in a conceptual way. You all know that. And in our previous video, we have started with thermodynamics subject and we have covered two chapters, basic concept and energy interaction of thermodynamics. In this video, we will be covering with first law of thermodynamics. Before start off with the definition of first law of thermodynamics, I do have an interesting example for you to understand this first law of thermodynamics in a better way. So what is the example is that you might all know about contraption event, which is conducted by many engineering colleges during their symposiums. What is the contraption event is that there will be a series of steps taking place and the energy transfer from one form to another. So either from mechanical to electrical, electrical to chemical, chemical to wind, wind to nuclear, and so on. The final understanding from those contraption event is that energy is conserved. Means that energy takes from one form to another, but finally the energy gets conserved within the particular system. So what is the definition of first law of thermodynamics is that if the state of adiabatically isolated system is changed by work, the amount of work is only function of initial and final points. Whereas the scientist Joule have another dimension for this definition of first law of thermodynamics. For a closed system undergoing a cycle, net heat transfer is equal to net work transfer. Mathematically, this particular definition can be represented as the cyclic integral of dq is equal to the cyclic integral of dw. If this particular cyclic integral value is a negative one or the positive one, what are the devices coming under this is that if it is a positive range, the devices is known as power producing devices. The classical example for this is heat engine. Whereas if the cyclic integral of dq equal to cyclic integral of dw fetches a negative one, the devices which comes under this category is called power consuming devices. Our household refrigerators and heat pumps are the example for power consuming devices, also compressor and so on. The law of conservation of energy is another name for first law of thermodynamics. The internal energy U of a system can change through two modes of energy transfer. These modes of energy transfer we might have covered in our previous video of energy interaction. We all know that the two energy mode transfer is either by heat or by work mode. Here del Q represents the heat supplied to the system by the surroundings and del W work done by the system on the surroundings, and del U is change in internal energy of the system. Mathematically, this law of conservation of energy can be represented as del Q is equal to del U plus del W. This is a practical example for law of conservation of energy. Here we have taken the IC engine cylinder with a series of piston arrangement. In this, the left side, the heat energy gets or the energy is supplied into the system, and in the right side, the energy is liberated out from the system to the surroundings, and the series of pistons available within the system doing a work. So there is an energy as well as work interaction takes place, and the law of conservation of energy happens here. And we have seen the change in internal energy of the various ideal processes. Say for example, constant pressure process, constant value process, isothermal processes, polytropic processes, and adiabatic process, how this internal energy change varies. For all the processes, the value is same, mCv T2 minus T1, except for isothermal process. In isothermal process, we know that the temperature is constant. Because of the temperature constant, there won't be any temperature difference. So there is no internal energy change in the isothermal process. Without the brain teaser, you all know our video won't get completed. So here is an interesting brain teaser for you all. So you put an air-filled rigid airtight can on a hot plate and add a certain amount of thermal energy to the can. What will you observe? In the question given data itself, it's clear that air-filled rigid airtight can. So there won't be any change in the volume. The volume is fixed. And if you supply a heat energy to the fixed volume, what happens is that the can can't get expanded more in the walls of the can, as well as the internal energy or the thermal energy inside the air, inside the can gets increased or shooted up. So this what's happened. If the can is a flexible container, in that case the walls get expanded, as well as there will be a increase in the thermal energy of the enclosed air inside the can. So if the can is a rigid one, there won't be any expansion of the wall. Only the internal energy or the thermal energy of the air trapped inside the can gets expanded out. If it is a flexible one, in that case the walls get expanded, as well as means that there is some work output we are getting it, as well as there is a internal energy change of the system. So another important terminology in first law of thermodynamics is that enthalpy. This particular term was coined by Molière during his experimental analysis. So what is that is, it is the total heat content of the body is referred to as an enthalpy. The example for it is how the ice gets converted into water. What is the chemical reaction behind? Means that how heat energy is supplied into the ice, particular ice phase of a water molecule to gets converted into liquid phase of water. So that particular heat exchange between a chemical reaction and its environment is known as enthalpy of reaction here. So what are all the outcomes of this first law of thermodynamics is that there are 4 outcomes. The first one is heat transfer is a path function. The difference between the path function and point function we might have covered in our previous video. The path function is a function which depends on the previous history or the past history of the processes. So heat transfer follows the previous history of the process. The second outcome is that internal energy is a property, means that it is a point function. The third outcome is that energy of an isolated system is always constant. You take an example of an isolated system. Say for example, we can take universe as an example for an isolated system. Within the universe, there will be the energy changes taking place from one form to another, but the energy is conserved. So the energy of an isolated system is always constant in this case, because of there is no energy transfer as well as mass transfer within the system to the surroundings. The fourth outcome is that perpetual motion machine of first kind is impossible. This is a crazy machine, perpetual motion machine. How far it is crazy is that it produces work continuously without observing any energy. So without we supply any energy, if a particular device produce the work, means it will be a interesting as well as most needed machine for our life. But practically, do you think this perpetual motion machine is available? Not at all, because it is impossible to develop a device which develops work continuously without observing energy. So this particular perpetual motion machine of first kind violates the first law of thermodynamics. So what are all the limitations of first law of thermodynamics is that this first law of thermodynamics is also referred as quantitative law, because it does not take into account the quality of the energy. Heat energy as well as work energy are the both energy modes we all know. In this, work energy is the high grade energy and heat energy is the low grade energy. This particular first law of thermodynamics does not give any distinct variation between this high grade energy and low grade energy. It simply tells us the quantitative law or the quantitative value for the heat as well as work. So this particular first law of thermodynamics does not deal with quality, which we will be dealing in the second law of thermodynamics part. Also, this first law of thermodynamics do not differentiate between the thermal energy available at higher temperature and thermal energy available at lower temperature. If 300 Kelvin is our thermal energy which is available with me, but that particular 300 kilojoules of energy available with me at 500 Kelvin and as well as in 300 Kelvin, there is a differentiation between this energy with the temperature difference. But this first law of thermodynamics does not take into account that and does not give any differentiation between this thermal energy at higher temperature and thermal energy at lower temperature. These limitations are rectified in second law of thermodynamics, which we will be seeing in our future videos. To get a clear picture of first law of thermodynamics, we will wind up with a problem. As a given data, 1 mole of ideal monatomic gas at 27 degrees Celsius expands adiabatically against a constant external pressure of 1.5 atmosphere from a volume of 4 decimeter cube to 16 decimeter cube. Our objective is to find the heat transfer, the work transfer and the internal energy. First of all, from the given data, it is clear that the monatomic gas expands adiabatically. As an adiabatic process, there won't be any heat transfer takes place, so Q gets 0. Our second objective is that work transfer. We all know the formula for work transfer is P into del V. Since we have to supply a constant external pressure for this particular system, we have supplying work to the system, so the negative signs is represented in the particular equation as work done is equal to minus P into del V. By substituting the value for pressure as well as the volume, we will be getting the value for the work transfer as minus 18 atmosphere decimeter cube. And the third objective is change in internal energy. According to law of conservation of energy, change in internal energy is equal to change in heat transfer plus the work done. So del U is equal to Q plus W. By substituting the value of Q and W in the equation, we will be getting the final value as minus 18 atmosphere decimeter cube. So I hope we have covered the first law of thermodynamics in this video. If you like this video, please do press the like button and suggest your valuable comments for our future improvisation. And viewers who haven't subscribed our channel, do subscribe our channel and get future notifications of all the thermo engineering subjects. Thank you.